So if something like this happens, you can check whether two things are independent. Okay? And now your task is to check the independence of following two random variables. Okay? So imagine I have x1, x2, x3 and x4, they are independent. And your first random variable is x1, x2. I mean, just don't write it, just have fun. Okay? Log x1 square, x2 square over absolute of x1 plus absolute of x2 bracket, okay, plus absolute of x1 cube, x2 cube and x1 power 4 plus x2 power 4. Isn't it? Looking good. And I'm giving you another random variable. So I have a z. Okay? Z is this. So sine. Okay? So sine x3 plus x3 squared plus x3 x4 plus x4 squared plus square root of x3 power 4 plus x4 power 4. So check whether they are independent or not.
Y and Z.
Y and Z. What should I do with that actually? How can I? So you have to verify this condition, Give it a go.
ये देखते हैं तो try it करें.
So maybe someone, maybe someone is a real nerd actually, and he can figure out some way to basically factorize things and come up with some way to verifying it. I can make your life more miserable. I can write something even more crazy actually. You can say that, okay, check the independence. So in measure theory, like that. Okay? This is something pretty good actually. So it just make your life easy. No matter what you have, depending on x1, x2, x3, x4, I can check its independence without even indulging into such calculations. Okay? So it makes your life easy. So measure theory is convenience. So not only it's powerful, measure theoretic probabilities, but it's convenient also. Okay? Makes your life easy.
So there is one trouble with probability that you told. This is actually one advantage of net theory.
Yeah.
This is not totally important.
Okay, so you can say maybe I can numerically check it, something like that. But, so if you have two ways to do it, do the same thing, okay? So from a computational point of view, for example, so one is computationally less complex and one is computationally more complex. You should prefer for the thing which is computationally less complex, which use your less resources. दिमाग जो है इस पे खपाने के लिए नहीं है necessarily. You have lots of other good things to do actually. 10 दिन यही calculate करते हैं. क्या होगा? I think the point. If there is something which is offering, ठीक है. The other thing, as I said earlier, that the measure theory or the measure theoretic probability unifies, but not be a good idea. Okay, because like calling it unifies, what do you call this, discrete versus continuous probability theory. So you don't have to indulge it to the discrete theory separately and continuous theory separately and do your things. You can define your things. So I mean, if you see, we define things differently in discrete, a little bit differently in discrete manner and then differently in continuous manner. Okay, maybe they are analogous, okay, that's a different thing, but there is, what do you call, different. So it unifies actually. So it just takes away this discrete versus multivariate and pseudo things actually. Okay. If you are still not convinced, then I'd like to throw a last thing. It's called the Banach Traski Paradox. How many of people have heard it? Huh? Banach Traski Paradox. There are books written on it. So the Banach Traski Paradox says, okay, or a version of it says, that if you have a sphere, okay, so if I have a sphere with some volume, okay, then I can do what? I can split it into the pieces, okay, some pieces, 4 to 5, 7, okay, some pieces, in such a way that if I reassemble these 7 pieces, I'll get what? The exact 2 copies of the same sphere. Ek copy. Wow. So this is a proven fact actually. So there's a mathematical. So even the size would be same, the volumes would be, so nothing is lost. So don't think that, okay, I can play a game actually. So if possible, next time I'll try to bring something or I'll try to show you a video actually. That guy is...
Resource.
Huh?
Resource.
No, not Vsauce is trying to explain it. Okay, but there is another video, okay, in which, okay, people are doing tricky things. But I think that it fits into basically this example. So I'll show you that. And maybe I'll share it.
Conservation law फिर कहाँ गया?
Sir, is it
Ask the physics.
यार, सर उसमें बड़ी होके सारा आगे बढ़ाए तो
Everything would be same. Nothing would be changed actually. Ek ka do. Now think about it. Sometimes.
है paradox है.
No, so you can prove a theorem actually. Doing it. So I can prove a theorem. The trouble is that you have to break this sphere into 7 pieces which are non-measurable, not measurable. And the question is, what is the meaning of non-measurability? So we'll do some examples of non-measurable sets actually. So you might have heard measurable things, but what would be the? It would be pretty interesting to see that what are the non-measurable things actually. Anyway.
Sir, we will talk about this at the end of our.
No, I'm not going to talk on this actually. I think it will be a huge diversion from it. But this is one of the consequences of measure theory, that you have to take this thing and break it into some non-measurable thing. So we will do the examples of non-measurable things actually. Okay?
We are getting motivated from this.
Okay, I'll try to give you, okay, not what do you call, okay, I'm not promising, but I'll try to give you a sketch of the argument that is going on. I mean, if you want to see a sketch, there is a beautiful video that this guy, Vsauce, what was his name? Vsauce has made. So it's a 30 minutes video. It's a 30 minutes animated video, more better than proofs actually. Okay, but it's not obviously rigorous. Okay, it's not obviously rigorous. To explain that how the heck it is happening actually. Okay? So see, let's just YouTube, Banach Traski Paradox. And I think these are the few things that we will find actually. So this Banach Traski Paradox, and there are many such concepts. And interestingly, in that same video, he also mentions that even people are doing physics based on this Banach Traski Paradox actually. The particles are popping out of nowhere actually already. Before that they are less in size and then the number and then they become,
Does it have any link with axiom of choice? Does it have any link with that axiom?
All of these theories that we are doing have a fundamental links with the axiom of choice actually, especially in analysis.
I was listening a lecture on that and first he was defining this thing.
Yeah. So it's a consequence of axiom of choice actually. So axiom of choice is used. So that's why people criticize axiom of choice, that it gives the crazy answers. Anyway, so I hope you will see this one day. But I would recommend you should see this actually. Okay. And I also recommend you to see a video by who? This 3 blue, 1 brown guy. Okay? So he has this video on music and measure. Music and measure. So must see this video actually. So music and measure. Music and measure. So see it also. So the thing is that there are lots of interesting consequences of all this. Okay. And again, measure theory is also so measure theory does not also have the links with what do you call the probability theory, but it has links wherever you have this integrals involved. And hence it has a deep link with function analysis as well. So it has links with function. And if you have links with the function analysis, it has links with the quantum mechanics. It's all about basically this. So let's do it. Why to wait? Enough of motivation. Want to have a break?
Yes.
Okay. Shall we have a break when you have this another event? अभी कर दो.
बाद में कर
दें. ताकि तो कोई इतनी खास बात तो बड़ी नहीं की है. Few simple things. ठीक है. Good. So let's get ready for the master. Master with a beauty.
Beautiful words. Beauty and the beast.
Beauty and the beast. So it's not the beauty and the beast, it's the beauty in the beast. I will begin with analogy. What is topology? So see, basic questions are always difficult. They are always very difficult. What is topology? If you know well that I'm not talking about the axioms, that okay, is that, and that, is that, and this and that.
Physical property.
Qualitative.
Physical. It's a qualitative study of geometry and so on and so forth. But I'm talking about the structured topology, not the set actually with the axioms. Actually. Why you need these axioms? So the topology is essentially a minimum set of axioms, or minimum set of defined through the minimum set of axioms. Minimum, this minimum is important. Minimum set of axioms that you need to define the continuity. Okay, this is what the key thing is. So you want to define continuity rigorously. So we need a certain set of assumptions, okay? And that's topology. Okay. So if you for example leave any of one of the, for example, axioms in topology, you will see that you can't define continuity. And because once you have continuity, then you can talk about, okay, what are those properties which are preserved under continuous things, because in topology theory you basically learned that all those properties which are invariant under continuous transformations actually. This is what the topology is doing. Okay? One thing. There is a role of continuity here. Okay? So it's like when you're doing probability theory, when you're doing integrals, there is a rule of continuity. What we want a structure, okay, or we want a notion actually which is weaker than continuity, okay, which is weaker than continuity, and that notion is so-called measure. I'll define it rigorously, but it's measure. So as we said that you have continuous functions. Now instead of continuous function, now I'd like to talk about the measurable functions. As I said, keep in view that all continuous functions are measurable. Okay, so what we want to do, we want to kind of relax things. Okay, so I'm not. So you see, one of the trouble that when you want to integrate, you want continuity somehow to integrate it actually. So wherever it is continuous, for example, so it's like wherever on a function, if there are discontinuities and there are some continuous, so there are places where the function is continuous on an interval. So what you want to do, you want to integrate on those continuous pieces and sum them actually, and then you get what you call essentially the integral of it. Okay, so you want continuity. Okay, so what we want to do. So again, so as I always say intuitively, when you stop, counting things actually. So you stop counting things. So when you stop, you start measuring. Okay? That's what the key thing is. So I can't count, that how many pieces of the small sugar, the pieces I have in 1 kg of, So I can't count them. So if you can't count it, measure it. Okay? So you have, it's pretty much the same thing. That okay, if things are not continuous, let's ask whether they are measurable actually by some source. But obviously we need to define what is the meaning of measurability in the first place actually. So the first thing that I am defining is so-called measure space. Okay? But it's going to have certain set of assumptions. But now it would be easy to answer, to understand for you that why you have these assumptions or axioms in, for example, measure space. Because I'll say that, okay, these are the minimum set of axioms that you need to define the notion of measure. Like the topology. The topology is the minimum set of assumptions that you need to define continuity. Okay. So, let's define what I mean by the probability space. Does anyone have book ID class? Yes, probability finance. Fill this class, please. Probability space. by a probability space. Okay. But let's not define things in this way. Let's not define things in this way. It's not a good way. So what I want actually in this way, I'm in a pretty difficult situation actually, because I don't want to lose the originality of measure theory. Okay, don't want to lose the originality of measure theory, and but like I want to do measure theory in such a way, all results of measure theory, important results of measure theory in such a way that our key example should be probability. So that's what essentially I would like to do actually. Okay, so what to do? So this guy is defining measure spaces better and probability spaces before actually. Okay. Let me define something. Let's define probability space. Let's define probability space. Let's do the way he's doing. Okay. Sometimes you run out of idea that how to start, and it's hard. That's a very bad thing when you learn from the young people. Not that young, but the people who have never good background actually themselves. Okay, in the sense of teaching actually. Okay, but when you learn from really experts, they just give you an awe. Actually. Oh, wow, that's starting. And I'm trying my best. I wish you can learn things, like people of level Kolmogorov and people like that. Anyway, so what's a probability space? So it's a triple. Okay, it's a triple. Omega sample space. Okay. And now there is no restriction on sample space. It could be anything. Okay. And set F, calligraphic F, and the map P. So I'll talk about each of them actually. So what I have sample space omega. So what is F? F is collection of subsets of omega, which we call events. Okay. So it's a collection of A's such that A's are subsets of omega. Okay. So power set is one example of F, but it's not necessarily power set. It could be some part of. Maybe I can say that this calligraphic F is a subset of power set of omega. This would be more better way to say it. Such that following conditions are satisfied. Okay. So these conditions are what? Number one, omega is in the F. Okay?
Define P.
I'm not defining, I'll define P. So let me just first define. So omega is in F. Okay. Already empty set is in F. Okay. And if I have a sequence, a countable sequence of elements from F, okay, then their union equal to 1 to infinity AI
Then F.
is also an F.
Sir, empty set.
So, okay, so it's like basically,
It's
I'll write the third condition, and then you will see that there is no need to write that empty set belongs to. So if I say empty set or sample space belongs to, so the third condition is that for each A in F, its complements, which is actually omega minus A, it also belongs to F.
ये देखा ना
Okay, something.
Defining.
It is. If it is generalizing continuity, there must be some connection. Are you getting the point? Okay. Okay. So if these three conditions are satisfied, you call F to be a sigma field. F is what? Sigma field. Okay? You give the name sigma field. Now what? So what this structure is, as I said, this is the minimum structure that you need to define the notion of measurability actually. Measurability. Which we are going to define later. And another thing is this. Is what? Okay. Forgot something. Okay, so essentially F is what? It contains omega. So therefore, so it's like since you have this, so therefore you don't need empty set there actually. So it's already there. This omega is there, its complement empty set is there. So you don't need empty set.